Wait, 1 gallon of gas is the same as the donut?
Yeah, the two, it's like 250. 250 for a single donut at Sheets. Yeah. Yeah. Yeah.
Why you don't go to Sheets?
Way. Yeah. So I think what Preston is telling me is I should have invested in donuts rather than Bitcoin. But maybe, I don't know.
I think you'll still make your money on Bitcoin.
I think I can get my money back in Bitcoin eventually, but I got to be patient. I don't know. But anyway, I will begin with a word of prayer, if I can. Dear Father, we thank you for this day again. I thank you for your students. Just ask you you be glorified in what we do, and that we'd understand a little more about your creation together today, Lord. In your name I pray, Lord Jesus. Amen. Let me get straight to it. I wanted to try to work through the calculation of the homology for like the circle. Maybe it's circle and disk. That'd probably be helpful for you guys, since I've asked you. So your homework problem is to calculate the homology groups for a sphere, all right? So essentially, if you can understand this calculation I'm going to do for the circle, you can modify my calculation to do the sphere, all right? So just a reminder that the mth homology group of the simplicial complex, we defined it to be the cycle, M chains, M cycle, oh, good grief, I've forgotten my language already. M cycles mod the boundary cycles. All right, and then the other big idea was that we can, ZMK, what was it? It was the span, well, it was, goodness gracious, I'm trying to remember. Was it CMK? Was that what it was?
No.
It is?
Yeah, ZM.
But what was CMK? Yes, CMK, vector space of all M chains, right? Vector space of all M chains. And then an M chain with no boundary is a M cycle. So this is not true. That's not true. They're not equal. ZMK is a subspace of CMK. So this is all M chains. In here, if sigma, let's say, is an element of ZMK, then the boundary operator acting on sigma is equal to 0, all right? So this makes, we call such a thing a cycle, an M cycle. On the other hand, BMK is a subspace of BMK. My bad. Let me try that again. ZMK. And if sigma is an element of BMK, then there exists alpha in the M+1 cycles such that what? The boundary of alpha rather, is equal to sigma, yeah? So, by the way, the boundary of alpha is equal to the boundary of sigma, which is equal to 0. So that's almost the proof that the boundaries are a subset of the cycles, right? They're a subspace of the cycles because every boundary is necessarily a cycle because the boundary operator squared is 0, all right? All right, so we can draw a picture, something like this. I don't know. Let's start at 3. C3 of k, and then there's C2 of k, and then there's C1 of k, and then there's C0 of k, and past that there's just 0, right? And there could be stuff above this in principle, I guess, but I don't think any of the examples we're working on go past this, okay? But here let us say this is the boundary 3, this is the boundary 2 operator, and the boundary 1 operator works here, all right? So that's the setup. So you guys tell me, in terms of like, what's this equation here mean in terms of usual like linear algebra? What does it mean? So sigma's in the cycle. That would say sigma is an element of what with respect to the boundary operator? Cur? Okay, that sounds helpful, but can you perhaps be more, cur of what?
Kernel, I guess, boundary M.
Boundary M?
Boundary M.
That feels right, yeah. So that means that's the case, right? On the other hand, sigma, an element of BMK, means what? See here, like, this right here is kind of instructive,
Oh, it's an M.
right?
M.
Sigma in the image of what?
Boundary M plus 1.
Right. All right. Furthermore, and here's just, the main thing is, remember we talked about the Betti number, the mth Betti number is equal to the dimension of the mth homology group, all right? And if that homology group is a quotient vector space, and it is, all right, then linear algebra tells us that that's actually the dimension of ZMK minus the dimension of BMK. So basically, if we can figure out the dimensions of the kernels and the images for these boundary maps, then we're good to go. And in fact, if we think about this, we can do a little bit better, right? This is actually what? The dimension of the kernel of what? Boundary M, if I trust you guys, minus the dimension of the image, or range if you like, of boundary M plus 1. At least that's what Rentland also says on page 147, so that's probably a good sign. All right? Although he uses K rather than M, which is kind of lame. All right, so let us think about this. We're trying to calculate the circle, which we'll call S1, right? Has this as its triangulation. And so we'll, for lack of imagination, do P0, P1, P2. All right, this is not the solid triangle, it's just, and to be clear, the simplicial complex I'm talking about here has what in it? We've got P0, P1, P2,
P0, P1.
P0, P1, P1, P2, P2, P0, you say, and then that's it. All right, because it's not the filled-in triangle, it's just the edges and the vertices. This is, in fact, a simplicial complex, and it gives us a triangulation of the circle. All right, so the theory that I'm not willing to prove for you in here it says that the homology of the circle is given to us by the homology of the triangle. But we can calculate it now, and let's do that. So the zero chains have the form like I heard that. C0, P0, plus C1, P1, plus C2, P2, right? Such that C0, C1, C2 are reals, right? The one chains here are, like, let's say B1 times P0, P1. And I'm ignoring the book, so, you know, I might differ in my formulas. You notice I just started numbering from 1 the second time because why not? It doesn't really matter as long as you're consistent in your numbering. And I think that's it. Right? That's it. Like, what's C2 of K? It's 0. Yeah. So 0 doesn't exist. Well, anyway, let's not get into that. All right. So what do we need to figure out? We need to figure out oh, man. That would have been maybe the most hilarious way of falling over the umbilicus. But, all right, so all righty. So I guess this is the boundary 0 map. I'm trying to figure out where to start. You guys help me out here. Start somewhere. What is, let's look at 1. C1K to C0K. So what's the formula? Boundary 1 of, what we got? What's a tip? Yeah. So we've got B1 times P1 minus P0 plus B2, P2 minus P1 plus B3 times P0 minus P2, I guess, which is equal to B3 minus B1 times P0 plus B1 minus B2 times P1 plus, what I'm doing is I'm writing it as a basis expansion, guys. B2 minus B3 times P2, all right? Notice that my basis for the 0 chains are the vertices, right? We take the vertices, formal linear combinations, we treat P0, P1, and P2 as linearly independent objects in our formal vector space, right? So like, so if I, you know, in terms of my usual linear algebra notation, if I had basis beta, P0, P1, P2, and if I had basis gamma, P0, P1, P1, P2, P0, P2, P0, right? These are my bases. The basis for C0 and the basis for C1, the vertices and the edges respectively, and this is the ordering I'm giving, then we can read from this that the matrix of partial 1 with respect to these choice of basis, right, is what?
The identity matrix, the first term is B3 minus B1. Or it's like the diagonalization, I guess, of B3 minus B1, B1 minus B2, B2 minus B3.
Well, all right, I guess I'll write it out then. So this, the gamma coordinate of that, gamma coordinate of that, the gamma coordinates of that. But the thing is, you can see those from this calculation here, right? Like, if I was to put this amounts to B1 equals to 1, B2 equals to 0, B3 equals to 0. All right? So what I have there, what I'm trying to say is, if I just look at the input of the first one, I only have that. All right? Which tells me that I've got this here. I'm sorry, I'm not saying it correctly. I don't, it's not that. I have, oh, good grief. Fine, let's write it out. No, I didn't. I mean, I didn't need to write both of these things, is the things, but I was hoping one of you would tell me what to do, but didn't happen, so.
We're dumb. I'm dumb.
So we're apparently dumb or tired, or dumb and tired. I can't really distinguish voices, but.
No, don't give her that. Don't give her that.
Daniel, are we over here? So, look, so the order of the basis is 0, 1, 2. That makes this a minus 1, 1, 0. This one, 0, minus 1, 1. And this is what you told me a second ago, Sam. Or not. 1, no, minus 1. So there you go. That's the matrix of partial 1. It's nilpotent. Ah, well, I mean, so then, like, the fundamental things we can use, guys, is the kernel, like the dimension of the kernel of the, the boundary, in this case, boundary 1, is the dimension of the null space of the matrix of this, right? So you can, kernel and null space calculations, we can figure that all out from just looking at the matrix. Is that matrix invertible? I don't know. Like, what do you guys think? No, this is definitely not invertible because if I subtract I think if I take if I add minus the first row to minus the second row, I get the third row, I think.
Yeah, it's zero determinant.
There's a linear, yeah, zero determinant. It's linear dependent. Of course, we could just, do row reduction. We get what? Minus 1, 0, 1, 0, minus 1, 1, 0, 1, minus 1, which is, of course, 1, 0, minus 1, 0, 1, minus 1, 0, 0, 0. There you go. I mean, we don't need to do all that much. We're only interested in dimensions. We don't need to do all this, all right? The point is, we can see that the dimension of the kernel is what? How many non-pivot columns are there here? 1, right? So the dimension of the kernel is 1. And while we're at it, what's the dimension of the image of the boundary 1 operator?
3 minus 1.
2. Yeah, 2. All right? So what else do we have to analyze? We can also analyze the boundary, well, the boundary zero operator, right? That goes from what? From C0K to 0, right? So what's the kernel of the boundary zero operator? It is C0K, right? So the dimension of the kernel of the boundary zero operator is 3. How about, well, so we got 0, we got 1. Anything interesting to say about 2?
It's got to just be 0.
So this is 0 at the moment. So what's the kernel? Yeah, the kernel of the boundary 2 operator is 0, right? So the dimension of the kernel 2 operator 0, and the image of the boundary 2 operator, what's that? It's also 0 because there's nothing to map. Yeah? Okay, so let's put this all together. We have figured out the dimension of all of the different kernels and everything, so let's work it out. What's the dimension of the 0th homology group? You guys got to help me out here. It's supposed to be what? Dimension of kernel 0 minus the dimension of image 1, right? And what are those? Dimension kernel 0, 0. Dimension of image boundary 1 was what? 2. Oh, that feels wrong. Don't like negative dimension. I think it's because I'm an idiot. I think 3. Yeah, 3. I like your choice of 3. That makes much more sense. Thank you. Muchas gracias. Yes. So the dimension of the 0th homology group, the 0th Betty number for the circle is 1. Now let us calculate. So this is beta 0 as it's called. Beta 1, that should be the dimension of the kernel of the 1 minus the dimension of the image of the 2 boundary operator, right? Now the kernel of the 1 we just figured out was 1, and the dimension of image 2 was 0, right? So therefore the first Betty number is also equal to 1. All right? And then past this point I think they're all 0 because like if we go to like beta 2 we've got dimension of kernel 2 which is 0, and then the 3 everything is trivial above 2, so it's all zeros past here if we go on up. So in short, we can summarize the homology group of the circle is equal to 1 if m is equal to 0 or 1 and it's 0 otherwise. Bum, 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 bum. That's where it stops. Oh, man. Man, that scam number keeps calling me. What's that?
The dimension of the space.
Oh, yeah. I'm sorry. I should say R. There we go.
So, where is it being a circle?
The circle is the fact that it's the triangularization is the triangle. So we blow up the triangle to the circle. That makes the triangle triangularization. I mean, that's a model, a discrete model, if you will, of the circle is the triangle.
But we just calculated that homology.
Triangle, right. But then the theorem is that gives us the so-called singular homology for the circle. So we can define the simplicial homology for the circle to be the homology of any simplicial complex which triangulates the circle. And the theory says that it will be the same no matter what our choice of triangularization is. It's independent of the orientation even, yeah. Mm-hmm.
Would it be true to say that we basically just make our problem easier by solving for the homology of anything homeomorphic to the sphere, or to the circle?
So you're saying they make the problem easier by calculating the homology of a simpler homeomorphic space?
Yes.
Yeah, I think that's right.
Space, and there's a theorem that says that they're the same.
Yeah. So a homeomorphism is a one-to-one. It's an invertible map which is continuous with continuous inverse, and that will preserve any topological feature of a space. In particular, it preserves the homology. So it's easier to calculate the homology directly of a triangle than of a circle because I haven't even defined the necessary things to calculate the homology of a circle. We could calculate the cohomology in terms of the closed forms mod exact forms, but that's also kind of scary because while I have found a particular closed but not exact form for you guys in the punctured plane, think about the question of how would I determine that's the only one up to some notion of congruence, that's kind of scary. At the same time, the calculation of simplicial homology is pretty straightforward once we have a simplicial complex. So, all right, next step. Let's do the disk. So to do the disk, we simply shade in the circle. And to do that, shade in the circle, likewise. Now the solid triangle is the triangularization of the disk. And our simplicial complex, we just throw in one more, namely P0, P1, P2, you see? Now everything that we said about the boundary 0 operator and the boundary 1 operator is unaltered. So we already know the start of the story is the same. But what's different is once we get to level 1 and 2, right? I mean level 2 rather. So notice now that if we calculate, boundary 2 acting on P0, P1, P2, I mean there's something to do there. And that's what? That is by definition P1, P2 minus P0, P2 plus P0, P1, okay. Now let's look at how does that compare to my basis here. It's a little bit funny. Let's see if we can if we're smarter now. Can we tell me what the matrix is of the boundary 2 operator with respect to, let us say, what? Oh, you may I need to do this? Okay, I'll allow it. I'm trying to think of what I need for I heard that. Oh, I guess I don't even have a name. Name. Gamma. So name is equal to it's the basis. It's the one-dimensional basis for the two chains, right? 2 chains. This math is so ghetto. Let's see here. Name. I'm sorry, I don't have the life experience to use that word. Let's see here. I think I'm making it worse. Let's see here. So we're going from a one-dimensional space to a three-dimensional space. That means that the matrix here is a what? The matrix is 3 by 1, right? So I think we're looking for a single column vector, aren't we? That's the matrix of this thing. This is kind of, I don't know why I'm doing all this. Sorry, guys. 1, 1, 1? All right. There you go. Exciting. So this shows us that the kernel of the boundary 2 operator is 0, and the image of the boundary 2 operator, the dimension, is 1, right? Because it doesn't, you know. All right, so when we, okay, so then we come back here and we calculate the dimension of the first homology group. What happens? Daniel, can you
-1.
come over here? Now that we're in the case of the disk, this is no longer 0. Now that we're in the disk, this has become 1. 1 minus 1 is 0. All right? However, exciting new case for this discussion, the disk, right? We have the dimension, my bad, beta 2, which is the dimension of kernel boundary 2 minus the dimension of image boundary 1?
3.
3.
Just give me 0.
So you get 1.
Oh, this is 0, isn't it?
Yeah.
Oh.
Yeah.
Oh, okay. That makes,
Which one?
oh, that makes sense, because the homology for the disk is more boring than the homology for the circle. Why? Because the disk has no holes. And remember, homology is in some sense about finding holes and things. And this one doesn't have a hole because we filled it in.
Is the homology of a space, it's like the M1 going to be 0 like most of the time? Is there a case where M isn't, for the M Betty, sorry, the 0th Betty number is not 1?
Is there a case where the 0th Betty number is not 1? Oof. If you had a point, if the space was just a point, maybe. I don't know. I wonder if it has something to do with it being connected. There's a neat calculation about the 0th cohomology group having to do with counting the number of connected components in the previous chapter. I didn't cover that, but there's so much more in Rentland to learn, than I have said in class, by the way. All right, let me go on here. So the other thing I should talk about briefly here. So guys, like in the homework problem, you're asked to calculate the homology of a sphere, and it does require actually a little bit of calculation. All of the linear algebra, you are totally free to use technology to do. I mean, it's a row reduction, so in the big scheme of things, that probably seems like an easy task in here, right? But there is an actual row reduction to do in the sphere one. So what would the triangulation of the sphere be for, like, I'm talking about exercise 5.3. What you'd want to do is you'd want to use the tetrahedron to triangulate the sphere. And then you're going to have, you have 1 3 chain, the tetrahedron, How many 2 chains you got? Well, you got 4 faces to the tetrahedron, so the C2K there is actually 4-dimensional. How many edges do you have for a tetrahedron? Yes, 6 edges. So the C1K is a 6-dimensional space. And then how many vertices? Well, there are 4 of those. So C0K is 4-dimensional. And so you got to look at the image, the boundary operators between these different spaces after you choose a basis, and find the dimension of the kernel and the image of each one of the ones, and then use the thing I wrote here that calculates the Betty numbers. That is all there is to it. And in the interest of you guys not wasting an inordinate amount of time on it, I will post the solution for you to look at, okay? So my apologies if you don't want to look at it, don't look at it though. All right, so. What's that? Oh, yes, that announcement I just made is helpful. So the Euler characteristic of a space, I'm going to call it M rather than X because it just seems wrong to use X and chi at the same time, is equal to the sum J equals 0 to the dimension of the manifold minus 1 to the power J of the jth Betty number. So this is the so-called Euler characteristic of a space. And he has some simple examples like Euler characteristic of a point is 1. Okay. The Euler characteristic of a line segment is 2 minus 1. Oh, I'm sorry. This is this right here is not from that. This is from something else. See, I'll explain what's going on here in just a second. This is what I'm not calculating Betty numbers for the triangle and these things, all right, or the solid triangle. Again, I will explain where these numbers are coming from here in just a second. Oh, this one's funky. This one's weird. All right. And that one is 4 minus 5 plus 1 equal to 0. So the theorem, which is proved on page 151, and I would love to prove, but I'm not going to, is, oh, come on. His notation. I did read this, and I have forgotten where that pesky thing came from. It must be in a previous chapter. Where are the alphas? Where are the alphas coming from?
Oh!
Is this some sort of movie reference or something? What's going on here?
I am. Oh no, I can't say these words.
This is recorded.
Oh no.
They don't know who I
Why?
am.
Oh man, where does he introduce the Euler?
You're looking in the
So the Euler characteristic comes from the bridges of Königsberg problem,
Yes.
which has nothing to do with Betty numbers on its face. Dang it, where did he? Yowzers. the Euler characteristic of K is equal to, I'll just write it down. I guess it's just here. Sum J equals 0 to the dimension of K. All right. Minus 1 to the J, alpha J, where alpha J is the number of J faces of K. All right, okay, fine. Those are different concepts, right? Betty number versus number of K faces. These are not obviously the same thing. But this is a theorem that says that the alternating sum of Betty numbers is equal to this alternating sum of the number of J faces. So like, I think the usual formula that you might have seen in high school perhaps would be like vertices minus edges plus faces is the Euler characteristic. So you can see that that's what's informing these calculations over here, right? Number of vertices, 1. Number of edges, 0, faces 0, so 1. Here we got 2 vertices, 1 edge, 2 minus 1. Here we've got 3 vertices and 3 edges, 0. Here we've got 3 vertices, 3 edges, 1 face, 1. Here we've got 4 vertices, 5 edges, 1 face, 0. All right?
It's not a tetrahedron?
Well, the tetrahedron,
Yeah.
what would the well, that's, I mean, fine. What is the, how many we got? 4 vertices, 6 edges, and 4 faces. We got ourselves 2. You can prove that the homology of the 2-sphere is equal to what? Well, I'll tell you what you're gonna prove. It's R. All right. M equals to 0 or 2, and it's 0 for M not equal to 0 or 2. All right. So this is the homology of the 2-sphere. So if we calculate the homology, the Euler characteristic of the 2-sphere, directly from the definition in terms of Betty numbers, we have, minus 1 to the 0, beta 0, plus minus 1 to the 2, beta 1. All the other Betty numbers are 0 for the sphere. Notice what this works out to. We work out to 1 plus 1, also known as 2. That is because the tetrahedron and the 2-sphere are topologically the same. They have the same homology. They have the same Euler characteristic. Or Euler characteristic. Thank you for that. That's very helpful. But, yeah. But anyway, so I think I could say more, but I'm going to let you guys explore the rest in the homework, and I will publish a lot of the solution to the homework on this stuff, because I think it's, you need to do the homework to better appreciate it, but at the same time, I don't want to, take 20 hours of your semester to do this homework. It took 10 hours of my previous semester to do it, so, by the professor to student multiplier, it would take 20 hours for you, right? No? No. You're like, we wouldn't let it get to that point, would we? We've got, we got CFOs to play with and stuff like that, but you guys aren't playing with CFOs, are you? No. Like you can go play Risk with them, or I don't know.
Tell them that the rate return is down.
Try to keep them off the train track, that kind of thing, Oh, I'm sorry, too soon? Let's hear. Nobody has taken a walk on the train tracks lately, have they? It's good. It's good. It's good.
So you're saying the sphere has two faces, right?
The sphere has two. What? All right.
Sphere has infinitely many faces.
All right. Let us talk about the integration of differential forms.
Okay.
And what I'm going to do to start with, rather than giving you the definitions, which I will project shortly, I'm going to do an example. Hopefully this example is not in your homework. Here we go. Example. What are we on? Example 1? Yeah. Consider the solid tesseract M, so 0, 1 to the 4th power, which is a subset of R4, and I'm going to give it coordinates x, y, z, w. Right? The boundary of that space consists of 8 three-dimensional faces, which stem x, y, z, or w equal to 0 or 1. Calculate the integral over that boundary of M of parentheses minus 12x w plus y times the tangent of z dx wedge dy wedge dz plus parentheses cosine cubed of y z squared w cubed plus 2x squared w dx dy wedge dz wedge dw close big parentheses. And then I have the following instructions. If you try to do this directly, then Loki wins. See past the hideous face of this problem. It's really quite easy. All right. So in other words, to do this directly, we would have to break this up into 8 triple integrals corresponding to the 8 faces of the tesseract. So we're going to say no to that. I would also wonder, am I right about the 8 faces? Like, it would be totally unsurprising if I was wrong about the number of faces of a tesseract. Like, I'm very bad at counting. So don't take it on authority that there are 8 faces of a tesseract. All right? Like, you know. Oh, this problem is also born of a time when I actually cared about Marvel a little bit. I really need to change this to something else. I'd say Lord of the Rings, but it seems like Amazon's tainting that too. And isn't Netflix about to do something hideous to Narnia?
Yeah.
We just need to read books, I guess. I saw something ugly about like Glenn Close playing Aslan or something. I don't. Meryl Streep. Oh, that doesn't make it better. So here's the deal, guys. This. Alpha.
Okay.
This is alpha.
Okay.
The generalized Stokes theorem, which I will begin to explain what it means today, says that we can trade the integral of a form over the boundary of a manifold for the integral of the differential of the form over the manifold. So we integrate over m d alpha. All right? So what is the exterior derivative here? It's not 0, no.
Close to it.
It's the 2.
Let's look here. This right here has a y and a z dependence. So when I take the exterior derivative of this, I end up wedging with y and z. Consequently, that term goes to 0. This over here, you got a y, a z, a w. Y, z, w. 0 also, because when I take the exterior derivative of this, I necessarily have a wedge repeated. So thankfully, we can ignore that. This, on the other hand, it could live on
Yeah.
because of the x.
And the first one.
So actually, we can focus our attention on, when we take the differential here, we only need to worry about the w. So we got minus 12x dw, wedge dx, wedge dy, wedge dz. And over here, plus 4 x w dx, wedge dy, wedge dz, wedge dw. And I think I'm going to put them in order, x, y, z, w, okay? So the second one's already in order. The first one, what's that? I did do that. Here. Let's get nuts. So we have
You get a positive sign.
the integral, 0, 1, 0, 1, 0, 1, 0, 1 of, yes, so I need to flippy flop. Oh man, I guess I just x, y, z. I need to move it over here, right?
Yeah, I think it's just positive.
That's a 3-fer. So that minus becomes a plus. We got ourselves a 12x plus 4xw dx dy dz dw. Fortunately, Calculus 3 is a prerequisite for this class, so you guys know how to do this. As you remember, all of the fourfold integrations you did in Calc 3. It's the same though, isn't it? Right? So, but look, these integrals are decoupled. So I can really just do integral from like 0 to 1 of this is what? This is x times what? Times 12 plus 4w, right? I can factor the x out. So I really have the integral of x dx times the integral of I'm not doing these in order, obviously. 0 to 1 of y dy. Oh, wait, there's no y here. It's just dy, right? That's an easy integral. Integral from 0 to 1 of dz, also a very easy integral. I recommend it. Integral from 0 to 1 of 12 plus 4w dw. So what we get is a half times 1 times 1 times 12 plus 2, also known as 7. Yeah, I'm very proud of this example because oftentimes when I make these up, they're very complicated and then they work out to 0 unintentionally, which is a great source of annoyance to me. But this one worked out to 7.
I think you dropped an X in your W.
I dropped up an X and a W. No, I factored it out. I factored it out. So if I have a product of functions of X and W and I have integration with rectangular bounds, I can rewrite the iterated integral as a product of integrals. It's true for 3 integrals. It's also true for 4. or 40, yep.
You have the opportunity to make that negative 52.
Make it, why do you want me to make it negative 52?
So that it'll be 47.
You want me to make it work out to 47? You know 45 squared is equal to 47.
45 squared. What?
What's your mod?
There's no mod. 45 squared is equal to 47. Preston has understood my stupid political math.
I think I know what
I don't-
Very good.
It
It doesn't make sense.
doesn't make sense.
No.
People say like,
It's stupid.
like there's people named Emma, they'll call them Emma squared, and it's like, well, that's not true.
Yeah.
It's just 2 Emma. So 90 is 47.
All right, let's see here. Okay, so let me, now that we have that example in front of us, let's look at the definition in my notes a little bit. I do want to talk about, I mean, the fundamental issue with the definition of the integral of a differential form. The question that is essentially begged, and the tricky part, is making sure it has the right independence of your choice of coordinates. See, because essentially you've got a differential form on a manifold, and you want to integrate it, right? So whatever notion you have of how to integrate this differential form, if you use a coordinate chart to form the integration, it begs the question, is your answer dependent on your choice of coordinate chart, right? So a lot of what's written in Rentland and a lot of what's written in my notes is to address that question. That, in fact, yes, the integration as we define it is independent of our choice of coordinate chart. This is provided that the manifold we're looking at has a volume form. What's a volume form on the manifold? Well, a volume form on the manifold, if we're talking about a p-dimensional manifold, we're talking about a, go away Windows security, I hate you. Let's see here. See, bagada. Oh, there, we just went through that. Oh, you guys can't see what I'm looking at. That's good. That's just as well. Let's see here. Come on. Not you guys, me. See here. W. All right. So, a little warning. This part of my notes is certainly from the time, I wrote this when I was a graduate student, teaching a class called Math 430, which is sort of the genesis of this class as well. And when I wrote these notes, I had a love of formulas. And so my approach to how to integrate differential forms is very much formula-based. I viewed the problem of how to integrate differential forms, like my responsibility as a writer of notes, my responsibility I felt like was to provide you a formula that you could calculate. All right? So I just asked the question, what formula could I write down to explain how to integrate a p-form over a space? And so the formulas that I have written down in these notes, I believe, are nothing more than the coordinate formulations of the pullback that you see in Rentland. Rentland tells you to take the differential form on the manifold and pull it back to the Euclidean space, which is serving as like the chart, the image of the charts for your manifold. You pull it back from the manifold back to Euclidean space. And how do you integrate a differential form on the Euclidean space? You just drop the wedges and do the regular integration. We're talking about